Welcome back to BiochemSerye Learning on the Go, ready for podcast 2E.
Tooey!
Today we're diving into the world of lipids.
Ooh, lipids.
Those essential molecules that are so much more than just fats and oils.
Absolutely. And we'll be tackling the definition and classification of lipids, along with some of their key functions. Think of this as your on-the-go intro to this fascinating family of biomolecules.
And for those who want to delve deeper, don't forget to check out the study guide on the BiochemSerye website.
Yes.
We've packed it with extra info and resources. You'll find the link in the description.
It's a great companion to this podcast, especially if you're prepping for an exam or just want to solidify your understanding.
All right, let's start with the basics. What exactly are lipids? What sets them apart from other biomolecules like carbohydrates and proteins?
Well, the defining characteristic of lipids is their insolubility in water. You know the saying, oil and water don't mix? That's because lipids are hydrophobic. They prefer to mingle with organic solvents like chloroform and benzene. They're the rebels of the biomolecule world, dancing to their own hydrophobic tune.
So they're like the cool kids who hang out in the organic solvent corner of the cell.
You could say that, but remember, they're not just hydrophobic. They're also esters of fatty acids with alcohols, and living organisms utilize them in diverse ways.
Fascinating. So how do we make sense of this diverse group? How do we classify lipids?
We'll be using a classic system adapted from Bloor, which divides lipids into three main categories: simple, complex, and derived.
Simple, complex, derived.
Yes.
Got it. Let's unpack these categories one by one. What makes simple lipids so, well, simple?
Simple lipids are essentially esters of fatty acids with various alcohols. They're the foundational building blocks, and we can further break them down into two main types: neutral fats and waxes.
Neutral fats, those are the ones we often hear about in nutrition, right? Like the fats we consume and store in our bodies.
Precisely. They're also called triacylglycerols or triglycerides.
Uh-huh.
Chemically, they're esters of fatty acids with glycerol.
Could you give us an example of a triglyceride, something we might encounter in our daily lives?
Sure, consider tripalmitin.
Okay.
It's a common triglyceride found in both animal and plant fats. It's a key component of things like butter, lard, and even some plant-based oils.
Okay, so tripalmitin is like a celebrity in the world of triglycerides. Now, I'm curious about the difference between fats and oils. Are they chemically distinct, or is it just a matter of their state at room temperature?
It all comes down to their melting point, which is influenced by the types of fatty acids they contain. Fats are solid at room temperature, while oils are liquid. But chemically, they're both triglycerides.
So it's like the difference between butter and olive oil.
Exactly.
Both triglycerides, but
Yeah.
one is solid at room temperature and the other is liquid.
Exactly. It's a great analogy.
Yeah.
Now let's move on to waxes.
Okay.
These are esters of fatty acids with higher molecular weight alcohols.
Waxes. I think of candles and waterproofing. Do they play a significant role in our bodies?
When it comes to human metabolism, true waxes aren't major players. However, they have a variety of other fascinating uses.
Like what? Give us some examples.
Think of lanolin, which comes from lamb's wool and is used in cosmetics. It's an excellent emollient, helping to soften and smooth skin. Or beeswax, used in candles, polishes, and even food wraps. And how about spermaceti oil, obtained from whales and historically used in lamps and lubricants?
Wow, those are some surprising uses for waxes. I never would have guessed that they're found in cosmetics and food wraps.
They're quite versatile. And while true waxes aren't central to human metabolism, there are other waxes that are important in biological processes. For example, cholesterol esters, vitamin A esters, and vitamin D esters play roles in hormone regulation and vitamin absorption.
Interesting. So simple lipids are like the foundational molecules in the lipid world, with a range of uses both inside and outside our bodies. Now, what about complex lipids? What makes them stand out?
Complex lipids, also called compound lipids,
Okay.
take things up a notch in terms of structural complexity. They contain additional groups along with fatty acids and an alcohol.
Uh-huh.
They're like simple lipids with an extra layer of flair.
Intriguing. What kind of extras are we talking about?
The extras can include phosphate groups, carbohydrates, or even proteins.
Wow.
These additions dramatically change their function and properties. There are three main types of complex lipids: phospholipids, glycolipids, and lipoproteins.
Okay, let's break down those three types, starting with phospholipids. They sound pretty important, especially with that phospho part hinting at a connection to phosphate groups.
They are indeed. Phospholipids are essential components of cell membranes.
Right.
Imagine them as the gatekeepers of our cells, controlling what goes in and out.
Okay.
They form a lipid bilayer that acts as a barrier between the cell's interior and exterior environments.
So they're like the bouncers of the cell, deciding who gets in and who stays out.
A great analogy. And their ability to form this barrier is due to their amphipathic nature. They have both a hydrophilic head, the phosphate group, and a hydrophobic tail, the fatty acid chains. This unique structure allows them to create a stable membrane in an aqueous environment.
That makes sense. So the hydrophilic head faces the watery environments inside and outside the cell, while the hydrophobic tails tuck themselves away in the middle of the membrane, creating a barrier.
Precisely. Now, there are two main types of phospholipids based on the alcohol they contain. Glycerophospholipids, where glycerol is the alcohol, and sphingophospholipids, where sphingosine is the alcohol.
Glycerophospholipids and sphingophospholipids. I'm sensing a pattern here with these names. Could you give us some specific examples of each type?
Of course. A common example of a glycerophospholipid is lecithin, which is abundant in egg yolks and soybeans.
Okay.
It plays a role in cell signaling and fat metabolism. As for sphingophospholipids, a well-known example is sphingomyelin, a key component of the myelin sheath that insulates nerve fibers.
So lecithin is like the cell's communicator, and sphingomyelin is the insulator that helps nerve signals travel quickly.
You got it. Now moving on to glycolipids.
Okay.
These lipids have a sweet tooth. They contain a carbohydrate molecule,
Okay.
a sugar, along with their fatty acid and alcohol components.
Okay.
Like phospholipids, they're important components of cell membranes, but they have a special role in the nervous system.
So glycolipids are the brain's favorite snacks.
You could say that.
Huh.
The carbohydrate portion of glycolipids acts like a cellular ID card, helping cells recognize each other. This is particularly important in the nervous system, where communication between cells is crucial for everything from thinking to feeling to moving.
Amazing. So glycolipids are like the name tags at a cellular conference, making sure everyone knows who's who. Are there any specific glycolipids we should know about?
Yes. Two important examples are cerebrosides and gangliosides. Cerebrosides, as their name suggests, are abundant in the brain, particularly in the myelin sheath of nerves. Gangliosides, on the other hand, are involved in cell signaling and communication throughout the body, playing roles in everything from immune responses to cell growth and development.
It's incredible how these lipids with their added sugar molecules take on such specialized roles. Okay, last but not least, let's tackle lipoproteins.
Okay.
I always hear about them in relation to cholesterol and heart health.
Lipoproteins are like the delivery trucks of the lipid world.
Okay.
They're combinations of lipids and proteins that transport lipids through the bloodstream. Remember, lipids are hydrophobic, so they need these special carriers to travel through our watery blood.
So they're like tiny lipid submarines
Yeah.
navigating the bloodstream and delivering their cargo to different parts of the body.
That's a fantastic analogy. And there are different types of lipoproteins, each with a specific cargo and destination. We have chylomicrons, which transport dietary fats from the intestines to various tissues. Then there's VLDL, or very low-density lipoprotein, which carries triglycerides from the liver to the tissues.
And what about the famous LDL and HDL? Those are the ones we always hear about in relation to cholesterol and heart health.
You're right. LDL stands for low-density lipoprotein, often called bad cholesterol because high levels are associated with an increased risk of heart disease. LDL transports cholesterol to the tissues, but if there's too much, it can build up in the arteries, forming plaque and increasing the risk of heart attacks and strokes.
And HDL is the good cholesterol, right?
Exactly. HDL stands for high-density lipoprotein, and it acts like a cholesterol scavenger,
Wow.
removing excess cholesterol from the tissues and transporting it back to the liver for processing. Higher levels of HDL are associated with a lower risk of heart disease.
Okay, so it's like a delicate dance between LDL and HDL, and we want HDL to be the lead dancer, keeping those cholesterol levels in check. So we've covered simple and complex lipids. You ready to move on to the last category? Derived lipids.
Absolutely. Derived lipids are a fascinating bunch. They're not as straightforward as simple or complex lipids.
Okay.
They're often derived from the breakdown of those other lipids, but they share some characteristics with lipids and play vital roles in various biological processes.
So they're like the spin-offs or the remixes of the lipid world, taking on new identities and functions.
A perfect way to put it.
So what are some examples of these derived lipids?
We have some familiar players here, like fatty acids, the building blocks of many lipids.
Right.
Then there are steroids, like cholesterol, which is a key component of cell membranes, and a precursor to hormones like testosterone and estrogen.
And don't forget about those lipid-soluble vitamins like A, D, E, and K, and ketone bodies, which our bodies produce during fasting or low-carb diets.
You're right. Those are all great examples of derived lipids. They may be smaller and derived from other lipids, but they play big roles in our bodies.
This has been a fantastic overview of the world of lipids. We've covered so much ground, from their definition and classification to the different types of simple, complex, and derived lipids.
It really highlights how complex and interconnected the world of biochemistry is.
Absolutely. Now, before we move on to part 2 of our lipid adventure, where we'll delve deeper into the fascinating world of fatty acids, let's do a quick recap of the 3 main categories of lipids.
Sounds like a plan. Remember, lipids are not just about fats and oils. They have incredibly diverse structures and functions, playing vital roles in virtually every aspect of life.
Okay, pop quiz time. Get those thinking caps on and see how much you've absorbed about these amazing molecules.
Let's test that lipid knowledge.
First question. What is the defining characteristic of lipids?
That's a fundamental one. It's their insolubility in water and solubility in organic solvents. This unique property sets them apart from other biomolecules like carbohydrates and proteins.
Correct. Next question. Which type of lipid is the primary energy storage molecule in our bodies?
That would be triglycerides, also known as neutral fats.
Okay.
They're incredibly efficient energy stores due to their high energy density.
You got it. Now, for a slightly more challenging question, what are the 2 main types of phospholipids based on the alcohol present?
The answer is glycerophospholipids and sphingophospholipids.
Okay.
The type of alcohol determines the overall structure and properties of the phospholipid molecule.
Excellent. Moving on, give an example of a glycolipid and where it's commonly found.
One example is cerebrosides, which are abundant in nerve cell membranes. The carbohydrate portion of glycolipids plays a crucial role in cell recognition and signaling.
That's right. Next up, what is the function of lipoproteins in the body?
Lipoproteins are the lipid transporters, carrying those hydrophobic lipids through the bloodstream. Without them, lipids wouldn't be able to travel to where they're needed.
Correct. Now for a quick recall question. Name 2 examples of derived lipids.
Easy. Cholesterol and fatty acids. Derived lipids are breakdown products of simple and complex lipids, but retain some lipid-like characteristics.
Perfect. We're on a roll.
Okay.
Next question. Why are lipids important in the structure of cell membranes?
That's because phospholipids form a bilayer that acts as a barrier between the cell's interior and exterior environments. Their amphipathic nature, with those hydrophobic tails and hydrophilic heads, makes them perfect for creating this barrier.
You nailed it. Now let's test your knowledge about cholesterol. What role does cholesterol play in the body besides being a structural component of membranes?
It acts as a precursor for steroid hormones and vitamin D. It's a vital molecule with multiple functions, showcasing the complexity of lipid biology.
Excellent. We're almost there. 2 more questions to go. What are essential fatty acids and why are they important?
Essential fatty acids are those our bodies can't synthesize, so we must obtain them through our diet. They're crucial for various physiological processes and maintaining good health.
That's right. And for our final question, how do lipids contribute to the insulation of our bodies?
Subcutaneous fat, that layer of fat under our skin, acts as a thermal insulator, helping to regulate body temperature and maintain a stable internal environment.
That's a perfect score. You've aced our lipid quiz. Give yourselves a round of applause.
Well done, everyone. You've clearly been paying attention.
This has been an incredible journey through the world of lipids. We've learned so much about their diverse structures, their essential functions, and their impact on our overall health.
I hope this podcast has sparked your curiosity about these often overlooked molecules. There's still so much more to discover.
And that's what makes biochemistry so fascinating. We're always learning, always uncovering new insights into the intricate workings of life.